Hey, all you cool cat and kittens. It's time for another amazing chemistry joke to awe your friends and impress your parents. Because it's just way too cool. Here we go. So, have you heard about a chemist who was reading a book about helium? He just couldn't put it down! Woo! Yeah, the jokes just keep getting better and better. So hopefully you were able to go do those molar volume problems. We're going to move on to the next type of math calculation when it comes to gases and stoichiometry, which is called the ideal gas law. So what is an ideal gas? It really doesn't exist, to be honest. But unless you're doing high-level research and you need to take into account the fact that gas molecules have some attraction and some repulsion, it doesn't matter. So an ideal gas is a theoretical gas composed of a set of randomly moving, non-interacting particles. It obeys all the gas law conditions, so all those things, Boyle's, Gay-Lussac's, Charles, all that good stuff. No matter how cold it gets, it doesn't condense into a liquid when cooled. And that is impossible, but that takes away that whole interacting thing. If you ever go on to chemistry and take this amazing class that'll blow your mind called physical chemistry, it's a combination of physics, calculus, and chemistry. Oh yeah, it's a really good time. I took it. Oh, there are no words for that. Anyways, to make a long story short, then you do take into account the fact that things are interacting. But at this level of the game, ideal gas law gives you good enough numbers unless you're doing some really specialized research. So what is the ideal gas law? A lot of times you'll hear it called perv-nert, not to be confused with pervert, okay? Perv-nert, kind of catchy. So what it says is if you take the pressure and volume of a gas, it is always going to be equal to the number of moles times R, which is a gas constant, times temperature. Let's look at those things a little bit closer. Gas laws usually mess people up because you have to be able to recognize what all the things represent. So P stands for pressure, and pressure we've already looked at can be kilopascals, atmospheres, millimeters of mercury, torr. You also kind of saw inches of mercury. So you have to be able to recognize the pressure. Volume for gas laws, in particular this one for sure, has to be in liters. So if we did Charles and Boyle's and that, as long as you were using milliliters every single time, it didn't matter. But when it comes to the ideal gas law, it has to be in liters. N comes into play. N stands for moles. Just like before, T is temperature, and it has to be in Kelvin. So if you're doing gas law problems and it's in Celsius, you have to add 273. R, we haven't seen R before. R is a constant. A constant is something that's always the same. And it's because when we look at gases and variables, there's a relationship, which is, and they're related by the slope of a line if we graph them. If we take the slope of that line and we set it up as like y equals mx plus b, there is a mathematical relationship there. That relationship is R. Now, R changes depending on the pressure. That's where it gets a little confusing. You have to pick the R value that matches your pressure. So when your pressure is in kilopascals, you have to use 8.31. When your pressure is in atmospheres, you have to use 0.0821. And when your pressure is either in millimeters of mercury or torr, they both are the same amount, then it has to be 62.4. So since R is a constant, if we are given three variables and we have R, we're going to be able to calculate the unknown variables. So the ideal gas law becomes one of those solve for X types of problems. Now what makes this different than the ones that you guys did before is that there's no before and after. So when we were doing like Boyle's and Charles and Gay-Lussac's and the combine, we had a P1 and a P2 and a V1 and a V2. There was always a before and after. Ideal gas law lets you figure out what's going on right now. So you don't have to know how it changes. It's what is going on right now. So here's how we go ahead and we solve these. We write out all the values given in the problems. We make sure those values are in the desired units, so they have to be in liters for a volume. They have to be in Kelvin for a temperature. We figure out which one we don't know, and then we use the algebra to solve for x, and we plug and chug. So here's an example. How many moles of H2 is in a 3-liter sample of H2 measured at 300 kilopascals and 20 degrees Celsius? Notice that you're given lots of information. Moles, liters, pressure, and temperature. When you were doing the other gas laws, moles was not involved. And notice there's no before or after here. That's how you know it's the ideal gas law. Because you're given pressure and volumes, it's talking about moles, and there's no before and after. So that's how you know you're going to be using the PERV-NERT in order to solve it. So again, here's what PERV-NERT stands for. And so now we're going to go ahead and fill out our variables and then solve for what's missing. So right away, I can tell that I don't have moles. So my N is my question mark or my X. It says that I have 3.1 liters. Liters is a volume, and it's in liters. And so I don't have to worry about converting it to liters, because volume always has to be in liters. Then it says 300 kilopascals. A kilopascals is a pressure. So I've got 300 there. And then it gives me a degree Celsius. A degree Celsius is a temperature. So I've got 20 degrees Celsius. In order to change it to Kelvin, I have to add 273. So my temperature is actually going to be 293 Kelvin. Always, always, always have to have your temperature in Kelvin, and it'll never work out. And then we have our R, is our other part. Since we are in kilopascals, the R value we're going to use is 8.31. So our R is going to be 8.31. Now I'm going to go ahead and plug what I have into my PV equals nRT equation. So 300 for pressure, 3.1 for volume equals N. We don't have. Our R value is going to be 8.31. And our T is going to be 293. So I'm looking for N. That's what I'm trying to find. So just like you do in algebra when you have one missing variable and everything was multiplied together, to get it by itself, I'm going to divide both sides by who's with N. So it's going to be 8.31 divided by 293. What I do to one side, I have to do to the other side. So 8.31 times 293 on this side as well. 293 times 8.31 is going to cancel. And so N is going to be equal to 300 times 3.1. That answer divided by 8.31 times 293. So I plug and chug that into my calculator, and I'm going to have 0.38 moles of H2. Now, if I wanted to make this even more exciting, instead of asking for moles, I could have asked for grams. And so if I would have asked for grams once I got to this point, then I would have used the molar mass to convert from moles to mass. But we won't go there for now. You're probably like, oh, thank goodness, Morty. We'll do one more example here. How many moles of O2 are in a 315 milliliter container that has a pressure of 12 atmospheres at 25 degrees Celsius? So again, it's asking for moles, and it's giving me milliliters, atmospheres, and temperature. So notice there's no before or after, and so this is going to be one of those PERV-NERT ones again. PV equals nRT. But notice our volume was in milliliters. In order to do this, your volume always has to be in liters. So I'm going to have to convert my milliliters to liters in order to fill this in for my volume, because my volume always has to be in liters or it won't work. Just like temperature always has to be in Kelvin. So we learned that 1 liter is equal to 1,000 milliliters. So in order to convert from milliliters to liters, you're either going to move the decimal 3 spots, or you can think about it as dividing by 1,000. So 315 milliliters, 1,000 milliliters equals 1 liter. And so if I plug and chug this out, it's going to be the same thing as 0.315 liters. Our temperature, we need to change it to Kelvin. And so in order to do that, you take whatever Celsius is plus 273. And so Kelvin is going to end up being 298 K. So after you figure out that it's ideal gas law, who you have and you don't have, sometimes you have to go that extra step and convert into the right units before you can actually plug in to your perv nerd. So let's go ahead and plug everything in. So pressure is going to be 12 atmosphere. Volume, we already figured out, was 0.315 liters. N is what we're looking for. R, this case, is for atmospheres. The R value for atmospheres is 0.0821. And then our temperature we figured out was 298 K. Ooh, that 2 is a little weird. Again, we're solving for N. So in order to do that, we have to divide both sides by 0.0821 times 298. I'm just going to go ahead and do the math that to simplify it a little bit. If I multiply those two together, it's going to be the same thing as 24.47. All I did was take and multiplied those two together. And what I do to one side, I need to do to the other side. And so if I go ahead and plug and chug all that out, my N is going to be equal to 0.15 moles of O2. And again, if I really wanted to, I can convert that to grams and I would know exactly how much or what mass of O2 I was going to have under those conditions. So that's pretty much ideal gas law, and that's what it is. It's another plug and chug thing. It's just that this doesn't have a before or after. Some of the pitfalls is to make sure that your temperature's in Kelvin, make sure your volume's in liters, and then you gotta pay attention to your unit in order to figure out what your R value is. Now you should be able to go back and do the second part of those problems. And then once you get those done, then you can watch the last video cast on how we combine stoichiometry with the gas stuff. Good times, people. See you soon. Bye-bye.